Okay, my lecture is about what is energy and how do renewables fit in. So we will discuss energy production today and how it will and should look like in the future because of some environmental concerns, and what will be the role of renewable energy in this change and how the required renewable energy production can be integrated to the energy system. Okay, so let's first look a bit on energy from the physical point of view, some physical basics. So energy physically is the ability to do work. And in a closed system, energy is always conserved. So a closed system meaning, for instance, the universe, or to quite a good approximation, the solar system. So a system which has like closed boundaries that energy cannot flow outside the system. And work changes the form in which the energy is, and this is called energy conversion. For instance, as you see here on the right side of this slide, the Olympic gold medalist Kaarlo Kangasniemi from Finland is lifting a weight, and he is using the chemical energy that he has acquired by eating food. He is converting that to mechanical work, which is again converted to the potential energy of the weights. But his muscles are a lossy energy converter because he gets energy loss to heat. He gets hot and sweaty, as most of you have probably got when you have done something similar. And practically all activity requires energy conversion. And usually the energy conversion has loss. But keep in mind that this doesn't mean that energy wouldn't be conserved. Energy is conserved overall in the closed system, for instance the universe, but not all energy can always be used by people. So the loss is energy which escapes the open system that people can manage. The open system in this case is the muscles of Kaarlo Kangasniemi and the weight, and also the chemical energy in his body. And an important thing of energy, as also other commodities, is that it has also quality. And electricity and fuels have higher quality than heat, and higher temperature heat has higher energy quality than lower temperature heat. So the main point here is that higher quality energy can be easily converted to lower quality energy, but not the other way around. And these economic energy production systems that people manage in the large scale in the world to produce energy can be described by these kind of energy chains. And the general form of such a chain is here in this slide. So there's the primary energy resource, which is kind of the raw material found in nature and used for energy production, for instance, coal, solar radiation, or uranium. And then it gets converted by people in power plants to energy carriers such as electricity or thermal energy in a district heating network. And this conversion almost always has some loss. And then the energy is transmitted by, in case of electricity, by the electrical grid, or in case of fuels, by tankers or natural gas pipelines, for instance, to the final consumption. And transmission also has some loss, but it's usually lots smaller than the conversion loss. And so this applies to this kind of economic energy production systems that people manage. So not, for instance, to food or some other ways how energy moves in the world, and we will not discuss this stuff in the lecture. So we will now focus on this large-scale economic energy production systems. But a nice fact to realize is that all this energy that is being produced this way and managed by people, it only corresponds to 0.02% of all the energy that is being used on Earth. And most of the rest is environmental heat from the sun, which keeps, for instance, our air hot, our air warm, our seas warm, etc., etc. But modern society can't function without this 0.02%, because we have much more advanced societies and we have better living conditions as humans than other species on this planet. And here we have the main energy sources used nowadays for energy production, and some example energy chains that how these energy sources are used. So the fossil resources are oil, natural gas, and coal. Then nuclear fuels to produce nuclear energy, mostly from uranium. And then we have the conversion processes, plants, refineries in case of fossil oil, the energy carriers, electricity, natural gas, petrol, for instance, transmission systems, and then the final consumption. For instance, combustion engines in cars for fossil fuels, gas burners for gas, electrical appliances such as dishwashers, fridges for electricity. So, what happens after this consumption? As we noticed already, energy will be conserved, so the energy will not disappear, but it will be lost mostly as waste heat. So, this energy chains, energy productions in essence is taking energy from these natural resources which are available, converting it, using the energy for some human need, and then releasing it as waste heat. And this electricity generation with plants, it always includes some loss. And in the case of thermal plants used for burning coal, biofuels, or also taking thermal energy out of nuclear reactions, this loss is relatively high temperature heat, which, as we noticed, has quite high energy quality, and it has value because it can be used for heat consumption, to heat people's houses, to heat people's domestic hot water. And this is called combined heat and power. And this is a way how these plants can be made very efficient, because you can also take advantage of the loss. And for instance, here in Helsinki, Finland, the district heating system is mostly operated by these combined heat and power plants in the city, which produce electricity and also heat to the district heating network. And here we have the renewable sources, biofuels, solar radiation, wind, hydro, and geothermal. So the definition of renewable energy is that nature renews the source as fast as people consume them. So, of course, all these energy sources are from nature, but these other sources, people consume them faster than nature produces new source. And out of these renewable energy sources, wind and solar are the so-called variable renewable sources, which depend directly on weather. So how much the wind blows at a given time, how much the sun shines at a given time. And these we will discuss later on in a more focused way. So here we have the recent history of energy sources, world primary energy supply from the beginning of the 1970s to 2012 in the world. So as we can see, the trend has been increasing, and this increase has come from increasing coal production, from increasing oil use, also from increasing natural gas, starting to use nuclear energy, and also slightly increasing the use of biofuels and hydro. So as we can see, the world in the 2010th decade relies very strongly on fossil fuels in energy production. And this is a major problem, because the carbon emissions, the CO2 emissions caused by burning fossil sources, are the main reason of human-induced climate change. And this is also the main concern on energy production in the future, so how to cut the carbon emissions. And here we have two scenarios prepared by the International Energy Agency, which is an intergovernmental organization, an expert organization working on energy. And they craft these kind of scenarios, which are their vision on how energy will develop, given the different policies. And they use these to look into how we can achieve goals, such as limiting global warming to 2 degrees, which climate scientists consider is kind of a safe limit. So here on the left, we have a scenario which will result in a global warming of 6 degrees. So basically just relying on the current energy production system and scaling it up. So trend in energy consumption will continue increasing, and the use of fossil fuels, oil, coal will increase. And so this will lead to the 6 degrees global warming according to the IEA, which can have very devastating consequences. And then here on the right, we have IEA's vision for achieving the 2 degrees goal, which is kind of a safe limit for global warming. So the main points here are that the total energy demand increase is kept very low, so almost constant, starting from around 2015. And then fossil fuels, such as oil mostly, is shifted to electricity by, for instance, electrifying traffic with electric vehicles. And the main idea is that the current fossil fuel-based system will convert to a system in which electricity is the largest energy carrier. So then the question remains, how do we reduce the carbon emissions of electricity production if it will be the largest energy carrier by 2050? So here we have again the 6 degrees scenario by IEA for electricity production now. So increasing fossil fuels, and here the 2 degrees scenario. So the main points are coal use is cut almost completely. So coal will produce very little electricity by 2050. This is a complete turnaround in the use of coal for electricity. And also what is left of coal electricity production by 2050 will use carbon capture and storage to limit the carbon emissions. And the other key point is a major increase in the use of wind and solar energy, flavored by these light green parts here. So in 2012, they are a very minor share of electricity production, but IEA envisions that in order to reach the 2 degrees global warming limit, they will produce 40% of electricity worldwide by 2050. And other measures include increasing the use of natural gas, starting to use carbon capture and storage, slight increases in nuclear production, slight increase in hydro production, and also increasing the use of biofuels in electricity production. So the key point regarding the end of this lecture is that the variable wind and solar electricity are envisioned to produce 40% of all electricity by 2050 in the 2 degrees climate change scenario. And integrating these variable renewable sources to electricity systems is not without problems, because the demand and supply of electricity in an electrical grid has to be in balance all the time. So production of electricity has to equal the consumption of electricity at all times in an electricity grid. And the two quantities in a power grid which indicate this balance are frequency and voltage. So both of these have to stay in given limits. And of course, this is nothing new to electricity grids. And but traditionally, only the consumption of electricity has changed, like uncontrollably and unpredictably. But now that we want to put a lot of wind and solar energy, there will be extra challenge, because also production will change such that it will not be completely controllable, and it cannot be predicted completely. So traditionally, the production has been controlled to meet demand variability and also failures in the system, such as power plants just stopping operating for some fault reason. But now that we want to put variable renewables, there will be need to also use other flexibility measures and not just electricity production. And these measures include storage, demand-side management, and interconnections. So these can provide flexibility without extra electricity production, which often tends to be fossil fuel based. And here we have an example of a specifically challenging week for renewable energy integration in the United States. So this red line is the original load, which the traditional power plants have traditionally followed. And then solar takes this share and wind takes this share, and what is left is a much more fastly changing, much less regular pattern to which traditional power plants have to respond, and it can even be negative, so which is new in electrical grids. So how much do we need to have this variable renewable energy, wind and solar, to really make this flexibility a big deal? So it's been estimated that around 5 to 10% of the total electricity production can be produced with these sources without much of a fuss for flexibility, just taking into account some basic things like not putting all of the plants to the same place so that there will be like a hotspot, but some geographical spread and the ability to control these plants in emergency situations and such. But when the share goes over 30%, then you really have to start to think about the system flexibility. And around 45% can be done without significant additional system costs. And as we just saw in the IEA 2-degree scenario, they envision wind and solar energy to produce 40% of electricity by 2050. So the global average will go over this 30%. In some areas there will be more and in some areas less, but this will be, if this scenario will be realized, this flexibility will become a very big deal in electricity production. And some countries are already past this limit. For instance, in Denmark, in 2014, wind produced 39% of all electricity production. So, as I just mentioned, there are these 4 ways to provide flexibility to electricity systems, and now we will briefly have a look at how they actually work. Here we have a kind of a semantic picture of what is called a smart grid. So the smart grid is kind of an electrical grid with this kind of information technology features implemented that are required, for instance, for this flexibility production timely and nicely. So let's first have a look at this traditional way to produce flexibility, which is by energy production, so by traditional power plants. So traditional power plants can be classified to base production, which is done usually by coal or nuclear. So these plants are not very flexible. They are designed and their economics kind of favors such operation that they are run constantly all the time. And then there are power plants that are used to follow loads and handle peaks, which tend to be hydropower plants, such as the one we see here, or gas burning plants or oil burning plants. These are the flexible plants. And these plants produce flexibility in 2 ways. By passive flexibility, so in these generators there's a large rotating mass which then converts the mechanical energy produced by burning these fuels or from this flow of water to it converts that to electrical energy. And these rotating masses have inertia, and this inertia kind of passively keeps the frequency in the electrical system to some extent. And also you need active flexibility, so you actively control these plants according to renewable energy production and electricity consumption. And these VRE plants, wind and solar electricity plants, can also provide some flexibility. They cannot be completely controlled. They can only be controlled downwards because the upper limit of their production is limited by the weather. And this downwards control, so-called ramping down, can actually be quite useful because these can be controlled very fast compared to many conventional power plants. And the relative energy loss, which is lost obviously when this ramping down is done, will be smaller than the relative power loss, which counts for flexibility. This can be understood by looking at some kind of schematic, simplified pictures of the production. So this is like 3 example days of a solar electricity plant. So this is a bright day, no clouds. Here we have some clouds which cut the production. And then here where we have a very cloudy day, which doesn't give that much energy. And then here we have a kind of a schematic picture of what it would look like throughout the year in Helsinki, Finland, where because of the northern location, the electricity production is concentrated to the summertime. So if we need to every now and then cut a bit of the production, say here, then on this day we need to cut here, and throughout the year we need to do some cutting here and there, we still have all this energy that is produced. So these VRE plants can also be useful flexibility sources to some extent. And then another flexibility source in the electricity system is demand-side management. So decreasing or increasing the energy use, electrical energy use, or shifting it in time. And this shifting is especially interesting because it can provide this demand-side management without affecting the final service which people need. So for instance, clean dishes form a part of an industrial product if there is some kind of storage in the process which can be used, and if the utilization rate of the process is less than 100%, because you need to be both able to increase and decrease the use. And so you can think of this as kind of a virtual energy storage which is 100% efficient, which cannot be reached by any actual energy storage technology. So how much can this electricity then actually be controlled? So let's look at the case of the country Finland, which has the peak load, which occurs in the winter time because of cold climate and the need to heat, of 14 gigawatts. So electric heating is the major flexibility source. It can provide around 25% controllable flexible load of the total peak load. And this can be made shiftable by taking advantage of thermal storages. For instance, water tanks installed in hydronic heating systems, or the envelopes of buildings can also be used. So the buildings can kind of, if the building structures are quite heavy, so for instance concrete buildings or such, the building envelope can store some heat and then release it when the heating is not used. And industrial processes can provide quite a bit of flexibility as well, especially grinderies in pulp and paper industry. So these are like mechanical devices which grind like pieces of wood into pulp. So as you can imagine, this is quite heavily energy intensive and very useful for this flexibility because you can store the pulp. So it's a shiftable load. And also electrolyzers, electric arc furnaces, rolling mills in metal industry can provide some, and also wet and cold appliances, people's dishwashers, washing machines, refrigerators can provide some flexibility. Energy storage. The basic principle is that you can store energy and there will be some loss in the process. So you charge, then you can store the energy for some time, then you discharge, but you always lose some energy in the storage. There are different technologies that can be used for this, and we will now look a bit more on the most important ones. So the pumped hydro energy storage is the one that is being used the most in the world in large scale, and it covers 99% of the large-scale electricity storage capacity in the world, and this is because it is the only economically profitable way to do electricity storage in large scale. The efficiency is around 70 to 80%, 65 to 85%. And then the traditional way, which is very much used in mobile appliances, in laptop computers, cars, in this kind of smaller scale electricity storage nowadays, is batteries. They can also reach quite high efficiencies. For instance, lead acid, which is used in cars quite a bit, can reach 75 to 85%. And lithium ion, which is used a lot in mobile devices and modern electric cars, can reach 90 to even 100% efficiency. And but the problem with batteries at large scale nowadays is that they are quite costly. So 1 kilowatt hour of storage costs several hundreds of euros. And then you can also take advantage of thermal storages by converting the electricity to heat and then feeding the heat to heat consumption from the storage, because at these low temperature levels that heat is demanded, such as in space heating demand, domestic hot water, the energy quality of the heat is so low that you can't really get electricity out of it. So the conversion only works in one way, from electricity to heat, and not vice versa. And the point why this is done is, of course, economic. So these are very cheap. For instance, this kind of very large 5,000 cubic meters water tank, which could be used in district heating networks, for instance, costs only around 3 euros per kilowatt hour, so like some percent of the cost of batteries. Here we have a picture of quite a large battery storage, which has 300 kilowatts of power, so it's nothing but lots of batteries connected together. And then the last way to achieve flexibility of the 4 ways, which I mentioned before, is interconnections. And these interconnections can be in the electrical grid. This can achieve geographical smoothing of variable renewable energy production. Here we have some examples. So here we have the correlation, which indicates how much 2 things depend on each other, and the distance between these wind turbine sites in Scandinavia. So as we see, the larger distance between the 2 wind turbines, the smaller the correlation between the 2 power production curves of these wind plants, and this decrease is quite dramatic. So this can be leveraged to smooth out geographically variable renewable energy production, because weather is not the same in all the places at the same time. And another example on solar electricity in the United States. So the red one is 1 solar plant, the blue one is the average of 5 close plants, and the black one is the average of 23 sites. So the black one is already quite smooth. And also with these interconnections, you can use flexibility resources from a larger area. For instance, in Denmark, they have a high wind electricity share, and they are using Norwegian hydropower to balance the variations in the production. And another, a bit more advanced way, maybe, to leverage interconnections between energy carriers. So this balance of supply and demand is not as much of a big deal for other energy carriers than electricity, because, for instance, gas networks, district heat networks, the network itself has some storage capacity, which is not the case for power grids. So again, by converting electricity to heat, converting electricity to gas, you can get to use this storage capacity and have less stringent balance requirements in these other energy carrier networks. And for instance, in Helsinki, Finland, the self-use limit, which is the maximum capacity of variable renewable energy production, which the city can consume itself without exporting, can be around 2 to 3-folded by using the district heating system, which is quite well established in this city. It covers over 90% of heat demand. And also electricity to gas, you can convert electricity with a loss to hydrogen or synthetic methane and use the storage capacity of the gas network. And then one maybe bit more advanced interconnection strategy is to use electric vehicles, the so-called vehicle to grid. So by using these batteries installed in these electric vehicles as energy storages at large scale. The point here is that these vehicles are idle for most of the time. They're staying at people's houses, they're staying at people's workplaces. And the charging window, the time that these vehicles stay in one place, is around 8 to 12 hours, while it takes around 1.5 hours to actually charge the battery. So there's a lot of flexibility in the time window to when the charging is actually done. Okay, to conclude, practically all activity that people, animals, plants do requires energy, and the sources can be fossil, nuclear, or renewable. And the IEA visions that wind and solar energy will have key roles in climate change mitigation, among other measures, in this 2-degree scenario for electricity production, which is shown here. And the large-scale use of wind and solar electricity will require more flexibility in the power grids. And production, DSM, storage, and interconnections can provide this flexibility. And as we can see in this scenario, the timeline is around 40 years. So achieving some very large turnaround like this in energy production will take lots of time. And people from my and your generations will work in key jobs required for this during this timeline.